Hi everyone, welcome back. We're going to be talking a little bit more about Laplace transforms here, laying down some more of the theory. In order to apply Laplace transforms to differential equations, we need to know how to deal with derivatives and antiderivatives in the Laplace setting, and that's what the theorems today deal with. Now, we've seen actually this first one before, so I'm not going to go through the proof of it as it's in one of the previous videos as an example, but it's still worth discussing again. So basically the situation is this. Suppose that we have a function f that's continuous and its derivative, f prime of t, is piecewise continuous and exponentially bounded. So we can expect now, because of that hypothesis, that f prime has a Laplace transform. Knowing that f prime has a Laplace transform, we might want to know what it is. And it turns out that it's related, unsurprisingly, to the Laplace transform of the original function f. So if that function f has Laplace transform capital F of s, then the Laplace transform of f prime will be equal to s times f of s minus f of 0. And that will be true for s greater than the maximum of 0 in a. All right, so the idea here is the proof idea here would be to just put this into the definition, and then you use integration by parts to get it to look like the original Laplace transform again. So you'll notice you have the Laplace transform of f, no derivatives involved here on the right-hand side, and you have the condition of f at 0. So this is going to fit very well with the initial value problems, because if we have a value at the starting point, then this is going to convert our initial value problems into something, again, with no derivatives, and that includes the initial conditions. All right, so now that's the first derivative. Then what about higher order derivatives? The second derivative, if f prime is continuous and the second derivative is piecewise continuous and exponentially bounded, then in terms of the original function f, its Laplace transform f of s, the Laplace transform of the second derivative will be s squared f of s minus s f of 0 minus f prime of 0. And you can get this by basically applying the formula from the previous part to itself. That would get you to the second derivative, and we get this kind of iterative form. So you can probably see at this point where things are going and conjecture what the formula might be for the third derivative, and assuming all of the appropriate conditions are met, so that the third derivative is piecewise continuous and exponentially bounded, so that it has a Laplace transform, then what will that be equal to? Well, it'll be equal to s cubed f of s minus s squared f of 0 minus s f prime of 0 minus f prime prime of 0. And that shouldn't be too surprising. That fits this pattern that we've been seeing. So all of that goes together pretty well. All right, let's try an example of this. Let's not try an example of this. Instead, let's take a look at the antiderivative. So if we want to find the Laplace transform of the antiderivative of a function, how does that work? So now let's assume that f is piecewise continuous and exponentially bounded. So that shouldn't have a prime in it there. So f of t is bounded by m e to the at, and it has Laplace transform f of s. Then what about the Laplace transform of the integral from 0 to t of f of u du? We're using u's there because s's are already being used, and we need a dummy variable in there. All right, so it turns out that that's equal to f of s divided by s, so the opposite of what we were seeing for derivatives. That shouldn't come as too big a surprise either. So how can we prove this? This one I do want to actually go through the proof of, because we haven't done that before. So let's begin by letting g of t, let's call g of t this integral from 0 to t of f of u du. So there's a couple of things that we might notice here. So first of all is that the derivative of this function is f of t, right? That's from the fundamental theorem of calculus, or the second fundamental theorem of calculus. And secondly, that g of 0 is equal to the integral from 0 to 0 of f of u du, which is 0, right? You're integrating from 0 to 0. All right, so now let's take a look at, let's say we have f of s. It's equal to, by definition, the Laplace transform of f of t. F of t we've seen is the derivative of g. And if we apply the theorem for derivatives, then this will be equal to s times g of s, where g of s is the Laplace transform of little g, right? So g of s is equal to the Laplace transform of g of t. And now we also know that g of 0 is 0. So we get the relationship that f of s is equal to sg of s, and that means that g of s is equal to f of s over s. And that's the thing that we're looking for, the Laplace transform of g of t, which is the Laplace transform of the integral from 0 to t of f of u du, is equal to f of s over s. So there's this relationship between the derivative of a function and multiplying by s in its Laplace transform, or anti-differentiating a function and dividing by s on the Laplace transform side. So the theme is that Laplace transforms are converting derivatives to multiplication by s. And that's going to be a huge help for us when we're trying to solve differential equations with these methods. So let's take an example of that. Let's apply the Laplace transform to an initial value problem. So I've just put one together. We're not going to follow through and solve this thing all the way, but I want you to see how it can be used, how this can be used to solve differential equations, basically, which is the whole reason that we're going into this. So we start with this differential equation, y double prime plus 4y prime plus 3y equals e to the 2t. Now, of course, we have methods for solving this, but we're going to try a different way. And it has initial values y of 0 equals 0 and y prime of 0 equals 3. So what we'd like to do is, so basically just assume if we have a solution for this, then it satisfies all of these conditions. We know there's a unique solution. We're going to try and figure out what that is. And we're going to do that by applying the Laplace transform to this entire equation. So we have the Laplace transform. Now let's change some width here. So the Laplace transform of y double prime plus 4y prime plus 3y is equal to the Laplace transform of e to the 2t. Now remember, the Laplace transform is linear. With linear combinations, you can just break it up across addition and constant multiplication. So we get the Laplace transform of y double prime plus 4 times the Laplace transform of y prime plus 3 times the Laplace transform of y equals the Laplace transform of e to the 2t. And we know that the Laplace transform of e to the 2t is 1 over s minus 2. And we're going to note here, let's call y of s, capital Y of s, is equal to the Laplace transform of y of t. Okay, so now we apply the formulas that we have for the derivatives. This is the second derivative of y, so that will be equal to s squared times y of s minus s times y of 0 minus y prime of 0. The Laplace transform of y prime will have 4 times s y of s minus y of 0 plus 3y of s, and that's equal to 1 over s minus 2. All right, so now because it's an initial value problem, we already know y of 0 and y prime of 0. We can plug in those numbers. And when we do that, we get that, that we have s squared y of s minus 3 plus 4s y of s minus 0 plus 3 y of s equals 1 over s minus 2. We can get all of our terms together that have a y of s in it. We get y of s times s squared plus 4s plus 3. And we can bring the 3 over to the other side, equals 1 over s minus 2 plus 3. Now notice that this thing that we have here is the characteristic equation, or the characteristic polynomial. That's no accident. In fact, in many courses, the characteristic polynomial is defined as the thing that happens when you apply the Laplace transform in this way to a linear equation. So finally, we get y of s is equal to 1 over s minus 2 times s squared plus 4s plus 3 plus 3 over s squared plus 4s plus 3. And so if we want to figure out y of t, what we need to do is figure out what function has this thing as its Laplace transform. So we need to find the inverse Laplace transform of this function on the right-hand side. To do that, we're going to try and break this up into simpler parts, and that's where the method of partial fractions is going to help us a lot. So that's the next thing that we're going to be covering, and that will allow us to find the inverse Laplace transform of this kind of expression on the right-hand side. And when we do that, we will have the solution to the differential equation without ever taking an antiderivative or anything like that. All of the work is baked in to the Laplace transform. So that's where we're headed with this. We'll talk about techniques for simplifying the right-hand side and ways of reversing the process to get the original function out of a Laplace function or Laplace transform